Hello, welcome everyone to another meeting of Symmetries in Newcastle. Our first speaker of the day is Townsend from University of Technology in Sydney, and he'll be talking about hyperbolic groups with k-Geodetic Cayley graphs. So the floor is yours, Kane.
Thank you. First of all, thanks to University of Newcastle. Good one. This talk is going to be on hyperbolic groups with a k-Geodetic Cayley graph, and this is joint work with Murray Olga, who's sitting there, and with it from there. So let's get started with what type of graphs we're going to be looking at. So let gamma be a locally finite simple connected graph. So fractional inverted that. And we're going to say gamma is geodetic if there are unique geodesic two vertices. So some examples, any sort of tree is going to be geodetic, and then a complete graph, so complete graph with 4 vertices is also geodetic, and then a non-example is a cyclic graph with an even number of vertices. So back in the 1960s, all asked the question to characterize all finite geodetic graphs. And if you look on like Wolfram alpha, then they'll give you a list up to 5 vertices, a classification of all of them, and then but for some other number of vertices, greater vertices, then there's no sort of complete answer here. But Murray and his post summer school student wrote some code and produced graphs up to, I believe it's 10 vertices. 11, okay. You can count how many numbers are there, and so that's the number of different graphs there are for each number of vertices for the geodetic. So like, yeah, but there's no sort of complete classification of geodetic graphs. And so we're going to sort of change the question a little bit and talk about geodetic, k-Geodetic graphs, and particularly with the Cayley graphs. So a slightly new definition, I guess, is gamma is k-Geodetic for some k greater than 1, if there are at most k-geodesics between any two vertices. Geodetic graph is also k-Geodetic for any k greater than 1. It'll include more graphs. A geodesic group with finite inverse closed generating set. Say the group is k-Geodetic with respect to the generating set if the Cayley graph is k. So this of course depends on the generating set, but sometimes I'll say G is k-Geodetic, and I will just that there is a generating set of them. Examples are cyclic group of order 4, that's generated by this element A, and if we choose all the generators, then other than if we choose all the elements other than the identity, then that will give us a complete graph, and so of course that is geodetic. And then if I choose the generator A and its inverse, then we'll get a cyclic graph with 4 vertices, which is not geodetic, but it is 2 geodetic. And so my only exercise for this talk is for each k greater than 1, give a group and its generating set such that the Cayley graph is k-Geodetic, but not k-1. Get to work. And so this, of course, is for finite groups, and so the question becomes a little bit more interesting when you look at
the exercise really improve.
Then tell us. Yeah, then tell us. Yeah. So some infinite looking examples. So we've got the free product of the cyclic group order 2 and cyclic group order 3, and so we've got the generator here, the C2 and inverse, and then we've got the generator and inverse for C3. All of the generator here. And so if you check, if I say highlight this one here, some verse here, then it's pretty clear that there's going to be a unique geodesic from between those two vertices. So I'm going to do a few little results to do with just purely graph theory stuff now. And the first one is a cute little lemma that highlights the difference between k-Geodetic graphs and geodetic graphs. So if we have a k-Geodetic graph and we've got k plus 1 distinct paths with the same initial point and terminal point, then there exists a path of length n-1 or length n-2. Prove this, then it's clear that none of these alphas are geodesics because there's k plus 1 of them. And then, so what we're going to do is consider one of these paths and at each step as we're going along, check if it's a geodesic or not. And the first time it's not a geodesic, then we stop there at that point. And then we look for what the real geodesic is from that vertex to where that path is ending. And that will give us a path that's either 1 less or 2 less. And the reason for that, and you actually draw a picture, is on step by step. And then suddenly
It's not showing.
oh yeah, actually do better color. It's on it's geodesic, and suddenly it's not a geodesic path that is a geodesic to there. And well, if this has length 1, 2, 3, 4, then this has to have length less than 4, so it's either 3, 1, and if it's 1, then we get a contradiction that up to this point will be geodesic. So it has to be 1 or 2 less. So hopefully that's pretty clear. And so the difference here between just geodetic graphs is you'd have only n-1 because you can't have sort of bygons going to the same vertex. From the same vertexes. Yeah.
Sorry, was there any relationship between the two?
Okay, so the n is the length of the path, and the so we've got k plus 1 distinct paths, and since you can't have them, they can't be geodesic because that would give you k plus 1 geodesic strings here. So the use for this lemma is to talk about these things that we call ladders, and I'm going to say that a ladder of some finite width has to have some bounded length. So suppose we have 2 disjoint geodesics in a k-Geodetic graph, and that they are distant m, some m greater than 0 for as many times as we like. We get a nice picture, something like this. So 2 disjoint geodesics, 1 and 2, and they're m apart some number of times. So what we can do is take a path from x0 to say yk, which is not here, but we could say there, and then there's k plus 1 different paths to this path within this graph that we've drawn. So you could go down to y0 and then travel along, go to x1, then down to y1, and go along, and so on. So that gives you k plus 1 distinct paths. So none of those are geodesics. And so that means there exists a path from x0 to yk that doesn't go through this some xk up here, and it has one of these lengths. And so what we do with that is we do that to one block, then we step along and do it to another block, and we get another shorter path, and we do that repeatedly, and then pigeonhole principle, and then repeat again, and we keep getting shorter and shorter paths. And eventually you get a shorter path from x0 to some xr that does go via yr. So you have some path from x0 to yr, something like that. And if you go up here, and it's a shorter path, which is a contradiction because we've assumed that this top row is geodesic. And so a corollary to this statement is there is a bound on the number of times that geodesics can be distance greater than 0 and less than m apart. And I just wanted to clarify something about these ladders. So in the we can do these statements are slightly more general. And so the two geodesics don't necessarily be distinct. They can look something more weird like this. So they've got meeting spots like here, but the key part is that they're distinct at these x2, y2 points is sort of I don't want to go into details of that because it gets slightly messy, but all the arguments are exactly the same in the group. And what we call these are asynchronously disjoint geodesics. Okay, so I'm going to start talking about some different classes of groups, which we are interested in for these k-Geodetic graphs. And so there's plane groups. And so plane groups are isomorphic to finitely many free products of finite groups and infinite cyclic groups. And I've given an example of that. Then we have virtually free groups. So virtually free groups, of course, have a free subgroup of finite index. And so that includes things like amalgamated products and H&N extensions with finite vertex group and edge group with. And the other group we want to talk about is hyperbolic groups. And so that Cayley graph is the hyperbolic space. And just to be extra clear, so we've got finite groups, free products of finite groups, and a free group, which is the infinite cyclic groups. Then virtually free groups contain those, and then hyperbolic groups contain those. So hyperbolic space, the sort of definition we're going to use is delta fin, just because it's the easiest to what I want to prove. And so hyperbolic space has delta fin geodesic triangles for some delta greater than 0. So all this means is we have these special points along that triangle, so that the distance here is equal to the distance here is equal. And the distance between these two sides as you synchronously travel along is always less than delta. So that's the definition of a geodesic triangle I'm going to use for hyperbolic space. And just to be clear, I've got this definition of non-degenerate triangles. So a non-degenerate triangle is something that will look like this triangle inscribed by these two vertices, and not something with these sort of extra parts on where they're joined together or have branching off Bigons or something like that. So you could define the degenerate triangle by any three vertices, but we want to exclude these types that are here. And I want to do the same for Bigons. So a non-degenerate Bigon would just be this these two parts and nothing that will look like this. Cool. So there's some classic questions for geodetic groups, and what I'm going to do is talk about what we know there, and then talk about what we know that we can work out for k-Geodetic groups. So the questions for geodetic groups are, what type of groups are geodetic? And the question is are they characterized if and only if they are plane? So are geodetic groups exactly those that are plane? And so this was asked in 1992. And so I've given an example of showing that all plane groups are geodetic. And the way that you do that is you just take the all elements in the finite group parts other than the identity. It's the generating set, and then just take single generators from the infinite cyclic parts, and that will give you a geodetic Cayley graph. And then in 1993, Papasoglu showed that if a group is hyperbolic and geodetic, then it is virtually free. So if we get inside that class of hyperbolic groups, then we can get further in and say that they're virtually free. But the problem is, are there geodetic groups that are not hyperbolic? And are there virtually free geodetic groups that are not plane? So I'm not going to talk about this too much until maybe the end of my talk. So what I'm going to do, spend the rest of my time doing, is generalizing sort of the things that we know about geodetic groups and doing that exactly for k-Geodetic groups. So we have our theorem. Let the Cayley graph be k-Geodetic. If G is hyperbolic, then there is a bound on the side length of non-degenerate geodesic triangles and Bigons, and then also G is virtually free. So G being hyperbolic means the geodesic triangles are delta thin. And then if we had some unbounded side length on our non-degenerate triangle, this would contradict our ladder parameter that we just showed before. So that's extremely straightforward, and the Bigons one is exactly the same because, well, a Bigon contains a geodesic triangle within it. So the next step is proving virtually free. And there's a characterization of virtually free that we want to use. And it has a so the characterization is there exists a finite set F of words in some finite generating set, so that if a word is not geodetic, if and only if it has a factor that is in F. And I've said the contrapart, the opposite there. So yeah. So a word is geodesic if and only if W has no factor in this finite set. Yeah. And so that's a result from Gilman, Hamilla, Holt, and Rees in 2007. So what I want to do now is consider some geodesic gamma. This vertex, and then we add another generator S to it, and we've got 4 different options. Either the new thing that we get is a geodesic and it's moved further away from this point. So that's case A. Case B is we move and we're the same distance away from this point. So there's a geodesic here, maybe it follows for a while, it goes up, but it's the same distance. And then C is it's actually closer, so that, and its length is 1 less than geodesic from here to here. And or we could just come back along this geodesic, so it's the inverse of the previous, the last letter in the word. So okay, so since we have that there's a finite number of non-degenerate geodesic triangles, since we know that there's a bound on the size of non-degenerate geodesic triangles, and since the generating set is finite, then there's a finite number of degenerate geodesic triangles. And so what we're going to do is define F by the union of the following words, gamma S, such that we take the cases from case B that give us a non-degenerate triangle, so it doesn't travel along this geodesic at all. Or B, which goes like this, And then also case D, where we've just got S and then S. And if we form F by that, then we're going to have exactly this set that Gilman, Camilla, Holton, Rees would want. So that proves that this proof needs to be virtually free. So the news is we can do even better than virtually free. So if G is hyperbolic and our Cayley graph is k-Geodetic, then we have some inspiration from K=1 case, which is from a paper in 1988, Adler and Otto, which says that the Cayley graph is geodetic, then if it's hyperbolic and an element has infinite order, then the centralizer of this element is an infinite cyclic group. So I've kind of converted their theorem into my sort of language. They're using rewriting systems, but I thought it'd be much simpler to introduce. And so what this does is it removes some of our virtually free groups that we've been worried about. So I've given a quick example here. So if we just have the simple amalgamated product of C4 with C4, then from here, AB is an infinite order element, but it commutes with all of G. And well, G is not Z, so we can't have G being geodetic for any generated Z. I kind of like this theorem because it's you're kind of not using the generating set in any way. It's nice. So the next part of my talk is generalizing this theorem to k-Geodetic graphs. So the first thing I want to talk about is primitive elements. So a word is primitive if there's no word u such that w is some power of u for some n greater than 1. And a lemma is the Cayley graph, let the Cayley graph be k-Geodetic, and then suppose u is primitive and each power of u is a geodesic representative for this element G. Oh, I've missed some of the definition. So let the Cayley graph be k-Geodetic and let G be an infinite order element. And then suppose u is a primitive element representing G, is a primitive word representing G, and u to the r is a geodesic representative for G to the r for all r greater than 1. And the centralizer of G is going to be generated by G. And I'm not going to go into the details of these proofs, so first just let an element, a word, be a geodesic representative for something in the centralizer. And you can see we sort of get this ladder structure, but we can't continue in this way. So the key thing is that this is indeed a geodesic because that's part of our assumption. And this is also a geodesic. And then, so this means that eventually these actually have to join together in some way. And if they join together, then they can bubble apart, but they can only do this a finite number of times. And there's a bit of sort of combinatorics on words, and the only solutions that you find are if this V is some power of U. And then the key sort of proposition is if we have a k-Geodetic Cayley graph and G an infinite order element, and we'll let Ln be the set of geodesic words for powers of G with respect to S. And if G is hyperbolic, then we can show that the union of Ln over all n greater than or equal to 0 is a regular language. So it can be solved by recognized by a finite state of one another. And the proof idea for here is I claim for any r greater than 0, there exists an n naught such that the length of this power of G is always going to be greater than R. So all powers of G after this this N naught are going to be outside of some sort of form. And the way I'm going to represent these diagrams is, since we're in k-Geodetic graph, I'm going to say there's some sort of like cloud of geodesics where there's all different paths to Gn, but there's a bounded number. And then the second claim is I can also choose an n star greater than n naught, such that when we add one more power of G, that its length has increased a little bit. And these are all sort of facts from the fact that S is a finite generating set. And you can't come into the ball sort of an infinite number of times. And then for large enough n, with that, I construct Gn, the geodesic for Gn star, and I claim that we can even create this unique geodesic path inside the middle of the path from 1G to Gn star. So the way you go about this again is, since we're in hyperbolic space, the distance between here is some bounded number, and then by the ladder corollary, we know that they have to join up. They could bubble apart again, but it can only happen a finite number of times. Otherwise, you get more than k-Geodesics. And so we have this sort of like cloud of geodesics here, cloud of geodesics here, but we do have this long straight path here. And then the next step is we consider Ln star plus 1 in two different ways. So the geodesics for Gn star plus 1. So we add a power of G to the other side. We add it to the left side and the right side. And since there's a bound on sort of non-degenerate triangles, we know we can set things up so that the geodesics from Gn star to 1G all pass through this beta. And the same goes to the other side. We can set up that all of these geodesics have to pass through beta. And since the size has increased, then we can see that all these geodesics, these alpha i's, is a prefix for mu j, and all the gamma i's are suffix for mu j. And then again, by some similar sort of combinatorics on words, we get this language for all the powers of n. So we've got this set, this finite set here. So the geodesics for L0 up to for G0 up to Gn star minus 1. And then we've got these geodesics here. And if you're familiar with regular languages, it's pretty clear that this is a regular language. And so the theorem that follows from this lemma and proposition is, if we have a k-Geodetic Cayley graph, and if G is hyperbolic, then we know that the centralizer of infinite order elements is infinite cycle. And the idea behind this proof is pumping lemma and through applying the lemma that we proved before. And just a little comment, because in some sense we are supposing that infinite groups can't be k-Geodetic unless they are actually geodetic. So I was just like, what happens if we join two Gn stars together? Then we get this sort of quicker way that goes via another path outside of gamma I and alpha j, which I thought was kind of not what I expected, at least. And so these are just giving you more powers of what this beta we found out to be. So I'm going to talk about some questions and problems that we have now. So we conjecture that a group is k-geodetic for some k greater than 1 if and only if it is geodetic. And furthermore, if G is infinite, then the Cayley graph is k-geodetic for some k greater than 1. Then the Cayley graph is in fact geodetic. And so the reasoning here is if you have two different paths in two vertices, and then by some sort of transitivity property, we think that you'll get a contradiction. You should be able to join it up with some other non-unique geodesics and keep piling those on, get up off the boundary. And then another question we have is, are groups with geodetic Cayley graph actually hyperbolic? And we currently don't know about this. We've tried a few things such as constructing the visual boundary or something like that using the Gromov boundary to prove something's hyperbolic, but we've had not much success with that. And then our other question is, why are these virtually free groups not geodetic? So something like the cyclic group amalgamated with the dihedral group of order 6. We don't know if this is geodetic or not. And it seems like there'd be no way to make it geodetic, but we've got sort of no sort of tools or anything to use to disprove it. And yeah, so other than that, I want to give like a quick sort of example with this one, is if we just take the sort of nice generating set for this group. So if I choose, let G be presented by AST, so A is the generator for C4, and then we have ST as the generators for the dihedral group, 2 reflections, and then we amalgamate the A squared with the STS, which is equal to TST. Then if I chose, say, this generating set, so include all the elements of the finite group of C4 and D3 and exclude the identity, then we have that AS is equal to A cubed multiplied with ST, both of which are geodesics and give you the same group element. So that's definitely not a geodetic choice of generating set, but why couldn't there be another sort of choice? I want to know. Answer I want to know. So other than that, thank you for listening, and hopefully we have some questions.
You Kane, do we have any questions? You're here or on Zoom, free to post them in the chat or unmute yourself and say it out loud.
Yeah.
So on your theorem about hyperbolic groups, you have this geodesic E and powers of G is regular.
Yeah.
Isn't that true for all geodesics in hyperbolic groups? That every geodesic coming will form a regular language.
Yeah, like I'm needing the language of geodesics is regular for hyperbolic groups, but I wasn't aware of language.
But it's a sub-language.
It's a summer and that's context free.
Yeah.
Yeah.
So like it's an intersection with context free and regular language, which we can't be sure that it's but yeah, I'll definitely have a look into that.
Questions? And
Okay, so you have this problem at the start. For every k, you want to find a group that's set so that it's a but not k minus 1 to that. Yeah, and then Murray said you're really interested in input. Does that mean it's done in the finite case? Yeah, so the finite case, you can find the k-Geodetic group. So you can find for the finite case, you can get a k-Geodetic group that's on k minus 1. Easy. It's not too hard. So take the cyclic group of order 2k and then take all the odd powers is the solution. This is between the things that are and it was an exercise. It's like a nice, if you cut it out, you could do it as an exam question for graph theory for second year students or something. Sorry,
One question from Max here.
Wondering, for instance, if you look at groups with infinite, say, then is the number of distinct geodesics between the two vertices going to say the number of distinct geodesics between two ends?
So I know at the moment our issue is with big ends. So if you have an accessible group and you can decompose it into one-handed things or zero-handed things, then yeah, so the thing that we need to remove is these thick ends, which comes up when we try to use the Gromov boundary for our groups. So the thing we're worried about is if we have some sort of geodesic array, and at some point, maybe each step along the array, there could be a geodesic that goes very far away and then comes back.
Actual elements of the boundary just have one geodesic, right?
Yeah.
Does there exist? I have examples. With more two or more geodesics between the two ends of the graph.
Yeah, I'm not sure exactly because I've done most of my work within hyperbolic groups.
Every time.
Yeah, the times T2, you have infinitely many geodesics between the. Simple and stupid sort of works. Questions for Kane? Well, if not, then let's thank Kane one more time. And now we have a lunch break.